Hello everyone, welcome to the first installment of the Advanced Problem Solving series. Today we will be solving problem 14 of the 2001 AIME 1. A mail carrier delivers mail to the 19 houses on the east side of Elm Street. The carrier notices that no two adjacent houses ever get mail on the same day, but that there are never more than two houses in a row that don't get mail on the same day. How many different patterns of mail delivery are possible? I chose this problem because it uses an interesting computer science technique called dynamic programming, or DP for short. This technique generally tries to solve smaller subproblems of a problem and then combine the results to solve the bigger overall problem. So now if you'd like to give this problem a shot before I present my solution, feel free to pause here. Okay, so at this point I'm assuming that you have given this problem a shot, so let's solve it together now. So first of all, we need a compact way to represent a series of houses which have gotten or not gotten mail. We will do this with a binary string in which a 1 at index I means that house I got mail. For example, if we had the string 1001, this would mean that houses 1 and 4 got mail, while houses 2 and 3 didn't. Also, we will define a string to be valid if it satisfies the conditions given by the problem. That is, no more than two adjacent houses got mail, and no more than two consecutive houses didn't get mail. So this is an example of a valid string, whereas a string like 110 would not be valid. Next, we will define a function f of n, which gives the number of valid strings of length n with the additional condition that each string ends with 1. Now I'm going to make a claim. F of n equals f of n minus 2 plus f of n minus 3. Why does this work? Consider a valid string of length n minus 2 and another valid string of length n minus 3, both of which end in 1. So for example, ... and then we have 1. And in total there are n minus 2 characters here. And another one, ... 1 with n minus 3 characters. 3. We can append 0, 1 to the first string and 0, 0, 1 to the second string to get a valid string of length n ending in 1. Of course, there are f of n minus 2 and f of n minus 3 ways to choose these two strings. So therefore, f of n equals f of n minus 2 plus f of n minus 3. As with any recursive relation, we would also have to have base cases. These would be f of 0 equals 1, since this is just an empty string with nothing in it. F of 1 equals 1, we just have this one string. And f of 2 also equals 1, because we just have this, we just have this one string of 0, 1. So now we can use this recursive relation to solve for any f of n. Note that our answer is f of n plus f of n plus f of n minus 1 plus f of n minus 2, where n equals 19, since any of the houses 19, 18, and 17 could have been the last to get mail. At this point, it's just calculations which we will brute force. So f of 0 equals 1, f of 1 equals 1, f of 2 equals 1, f of 3 equals 2, f of 4 equals 2, f of 5 equals 3, f of 6 equals 4, f of 7 equals 5, f of 8 equals 7, f of 9 equals 9, f of 10 equals 12, f of 11 equals 16, f of 12 equals 21, f of 13 equals 28, f of 14 equals 37, f of 15 equals 49. F of 16 equals 65. F of 17 equals 86. F of 18 equals 114. And f of 19 equals 151. Sorry, that should be a 5. So finally, our answer is f of 17 plus f of 18 plus f of 19. So I'll just write that here. Which comes out to be 351. So therefore, there are 351 possible patterns. So as always, thank you for listening, and if you have any questions, feel free to leave them down below in the comments. I hope you all have a great day.